In this podcast, I am going to present our work on the heat wave model for constructing three-dimensional mortality improvement scales with measures of uncertainty. The production of this podcast is sponsored by the Society of Actuaries 2017 Centers of Actuarial Excellence Research Grant. Let me begin with an outline of today's podcast. So I will spend some time to explain what are mortality improvement scales. I will review existing mortality improvement scales, and based on these, I will develop my research goals, explain the proposed methods, and finally, draw a conclusion. So, what are mortality improvement scales? The purpose of a mortality improvement scale is to determine an allowance of future mortality improvement in actuarial pricing or reserving. A mortality improvement scale specifies the annual percentage reduction in each specific mortality rates. It is largely formula-based and practical in the sense that they can be programmed very easily in Excel, for example. And there are quite a few existing mortality improvement scales. In North America, we have Scale AA, the scale in the valuation basic table, Scale BB, CPMB, AMP 2014, AMP 2015, and the newest AMP 2017. And in the United Kingdom, we have also seen quite a few mortality improvement scales as well. Let me review some of the existing mortality improvement scales. In North America, in the past, the most frequently used mortality improvement scale should be the Society of Actuaries Scale AA. Now, Scale AA was developed in 1994. It specifies the annual percentage reduction in age-specific mortality rates. And I'm going to denote the specified percentage reduction for age X as AAX. And on this diagram, I've shown the scale factors for both genders at different ages. It is important to note that these scale factors change with age but not with time. And because of this, we call Scale AA a one-dimensional mortality improvement scale. There are some problems associated with one-dimensional scales. First of all, they are typically derived heuristically, either by trending past observations or by using some sort of actuarial judgment. And we have also seen that Scale AA did not perform very well. Now, in this table, I have compared the scale factors in Scale AA against the actual reduction in the decade following the introduction of Scale AA. And we can see that Scale AA seems to have seriously underestimated the actual reduction. Okay, one more problem. And to explain that problem, let me first introduce the concept of a mortality heat map. And on this diagram, I've shown the mortality heat map generated using historical mortality data from the England and Wales male population. So, on the horizontal axis, we have calendar years. On the vertical axis, we have age. And the colors in this diagram represent the level of historical mortality improvement. The warmer colors represent higher mortality improvement, and the colder colors represent the opposite. So we can see that these colors change with age, they also change with time, and we also see some diagonal patterns in this diagram. Now, because each diagonal in this diagram represents a specific year of birth, these diagonal patterns therefore represent the so-called cohort effect of mortality improvements. If we use a one-dimensional projection scale, we will end up with a projected heat map like this. It has only variation along the vertical dimension, i.e. age, but not at all with time. And obviously, it does not capture any cohort effect. So, a one-dimensional scale is not sufficient to capture what happened in the past and what may likely to happen in the future. And to mitigate this problem, a multidimensional approach has been proposed. In a multidimensional scale, we have different scales for different time horizons. In particular, we have a short-term scale for the near future. These are generally short-term rays to reflect the rapid mortality improvement that has been observed in recent decades. And in the long-term scale, we have very low scale factors that are derived on grounds that rapid mortality improvement will not last forever. And then finally, we have a mid-term scale that blends the long-term scale and the short-term scale. And the consequence of such a scale is that the scale factors depend on both age and time. Okay, so here are some existing two-dimensional mortality improvement scales. We have the Canadian Institute of Actuaries CPMB scale, which is defined like this. For the short-term scale, they have the annualized mortality improvement rates that were observed between 1999 and 2008. For the long-term scale, they use the long-term actuarial assumptions in the 26th Canadian Pension Plan Actuarial Report. For the mid-term scale, they use linear interpolations. And then we have the Society of Actuaries AMI 2014. In AMI 2014, the short-term scale is calculated using the realized smooth mortality improvement rates in 2007 for the Social Security population. For the U.S. Social Security population, for the long-term scale, they generally use a 1% per annum for all ages, and for the mid-term scale, they use a double cubic interpolation to blend the short-term rates into the long-term 1% rates. And for the UK Institute and Faculty of Actuaries phototype model in 2009, the short-term scale is defined as the smooth improvement rates for the English and Welsh population realized in 2005. The long-term scale is left unspecified. They use 1% and 3% per annum for illustration purposes only. And the midterm scale is developed using some sort of cubic polynomials. These two-dimensional scales are obviously more flexible than one-dimensional scales such as scale AA, but they're still subject to some limitations. First, the long-term rates in the previously mentioned scales are determined by either expert judgments or simply by making reference to the assumptions used in all the jurisdictions. Secondly, the direction of the transitional phase is also decided by expert judgments only. And finally, and probably the most importantly, is that these scales do not give any measure of uncertainty surrounding the best estimate, and with no measure of uncertainty, we are unable to develop margins for adverse deviations using the existing scales. Our research goals are developed to mitigate the problems that are found in the existing two-dimensional scales. In particular, we consider a model-based approach. We develop a model-based approach to constructing two-dimensional mortality improvement scales with various features. Number one, in line with the spirit of the existing two-dimensional scales. Number two, involves less subjectivity. Number three, has the possibility to include measures of uncertainty. And number four, is practical. Before we developed our new model, we experimented various existing stochastic mortality models and see if they can satisfy the criteria I set out earlier. So the existing models include the Lee-Corder model and the Ranshall-Haber model. These models assume that historical mortality rates in log scale can be represented by a combination of different parameters. In the Lee-Corder model, we have alpha and beta, which are related to age, and kappa, which is related to time. In the Ranshall-Haber model, we have age-related parameters, we have time-related parameters, and we have the last parameter gamma, which is related to t minus x, current year minus current age, which represents the year of birth of individuals. So we have gamma parameter being a cohort-related parameter. We have the class breakdown model. We have also experimented an extended version of the class breakdown model, which is commonly known as Model M7. So let's see if these models can satisfy our criteria. This model shows the projected mortality improvement rates implied by the Lee-Corder model. So we see that the projected rates shown on the right-hand side of this diagram do not extend naturally from the historical rates, and because the Lee-Corder model has no cohort effect term, it does not capture any diagonal pattern, and in fact, it only captures variations along the age dimension, but not the time dimension. All right, Model M7, a more sophisticated model, which in turn produces a more sophisticated pattern of projected mortality rates, but still, the projected improvement rates do not appear to extend naturally from the historical rates. So to sum up, the existing models do not quite fit the bill. We need to develop a new model to achieve our research goal. So our proposed model. We call our proposed model the heat wave model. This model is comprised of two key components. The first component captures background improvements. Now, background improvements are similar to the concept of background radiation in physics. We're assuming that long-term mortality improvements are background improvements that always exist, and we model these improvements by using typical time series processes. And secondly, the model captures heat waves, which correspond to the rapid mortality improvements that are observed in recent decades. These heat waves are expected to diminish over time. Now, the heat wave components also determines the speed at which mortality improvement rates converge to their ultimate or long-term values. Okay, with these ideas in mind, the model is constructed parametrically like this. So on the left-hand side, as in the Lee-Corder, we have the log central death rate at hx and time t. And on the right-hand side, we have two key components which are color-coded. Now the brown component is just the basic Lee-Corder structure. We assume that the time-varying parameter kappa t follows a random walk with drift d, as in the original Lee-Corder. This component captures the background mortality improvements. Secondly, we have a parametric function, f. Now, this function captures the heat waves. This function contains three parameters, and I will explain the functions of each of these three parameters in a moment. I think this model can be easily understood by considering its differential form, i.e., the change in log central death rate at hx between time t-1 and time t. So, in differential form, the model can be written in a very compact form like this. First term, beta 1x times t, again represents the long term, i.e. the background improvement rate. Second term, with the function f, which reduces to 0 as t approaches infinity, captures the heat wave. Now, With the differential form, we can easily see that parameter mu in the function f determines the center of the heat wave. Likewise, sigma controls the speed at which the heat wave tapers off. And finally, parameter h represents the mix between period and cohort effects in the heat wave, and I will explain this in more detail in the next few slides. Finally, we allow different ages to respond differently to the heat wave, and that is done by introducing a second age-specific parameter, beta 2x, into the model. Functionality of parameter h. So let me explain the functionality of h by considering two extreme cases. In the first extreme, when h equals 0. Now, in this extreme, the center of the heat wave is completely independent of time, so the heat waves will be lined up like this. So that means the heat wave is purely a time-related phenomenon. It has nothing to do with cohorts. But in the other extreme, when h equals 1, the center of the heat wave will move to the right by 1 as h increases by 1, and in effect, the heat waves will line up perfectly diagonally like this. And remember, a diagonal in the heat map represents a year of birth. So if the heat wave lines up in this way, that would mean the heat wave is purely a cohort, i.e. year of birth related effect. So if h is in between 0 and 1, we can conclude that the heat wave is a blend between period and cohort effects. Before I present the estimation results, I wanted to mention that the heat wave model is very practical. Typically, in a mortality improvement scale, scale factors are defined as annual percentage reduction in mortality rates. And with a little bit of algebra, we can see that the annual percentage reduction in age-specific mortality can be expressed in this form, which boils down to a function of age and time. So this thing can be programmed in Excel very easily given the estimates of all of the model parameters. Okay, we have estimated the heat wave model to the historical data of the male population of England and Wales, and we obtain these parameter estimates. So we have sigma, so we have an estimate of sigma being 16.9 something. So as you may recall, the value of the normal density function reduces to almost 0 at true standard deviation. So based on this parameter estimate, we can conclude that the transitional phase is approximately 2 times 16.9, which is approximately 34 years. And we have an estimate of h being 0.82 something. This estimate indicates that the heat wave for this particular population is a blend between period and cohort effects, with cohort effects being more significant. And we have the estimates of other parameters, including alpha x, beta 1x, beta 2x, and kappa t. Okay, so let me do a zoom in of kappa t, and I would like to also compare the kappa t from the heat wave model with the kappa t generated from the original Lee-Carter model. What we can see, notably, is that kappa t, we can see that the estimates of kappa t in the heat wave model are a lot more linear than the kappa t's from the original Lee-Carter model. That being said, apparently the heat waves have captured some of the nonlinearity in the cohorts from the original Lee Corder model. So let's see how well or how badly the proposed heat wave model performs. All right, so I am showing once again the projected mortality improvement rates generated from the original Lee Corder model. And as I mentioned previously, this is not an ideal projection because it does not capture any cohort effect. It's only one-dimensional with variation only across age but not across time. It does not give a natural extension, what we have experienced in the past to the future. Okay, so now we have the mortality improvement rates generated by the proposed heat wave model. All right, so we see that the projection generated from the proposed model appears to be a much more natural extension of what happened in the past. It captures age effect, i.e. variation along the vertical dimension, time effect, i.e. variation along the horizontal dimension, as well as cohort effect, i.e. variation along the diagonals. So finally, I wanted to give a remark on the long-term, i.e. the ultimate improvement rates implied by the heat wave model and the original Lee Corder model. Now remember, in the original Lee Corder model, we do not distinguish between short and long-term rates. So in effect, the long-term mortality improvement rates are still quite high, as indicated in the red line in this diagram. Well, in the heat wave model, we distinguish between short-term and long-term improvement rates, and according to the estimation results, the long-term improvement rates implied by the heat wave model are significantly lower compared to those generated from the original Lee Corder model. It is also interesting to see on an age-by-age basis how the heat wave model is different from the original Lee Corder model. So we are going to look at 3 different ages: age 60, age 70, and age 80. So for age 60, the Lee Corder model implies much lower future mortality rates compared to the heat wave model. But then, for age 70, the situation is changed a little bit. The heat wave model implies lower mortality improvement rates in the near future, but then in the distant future, the opposite is true. For age 80, the improvement implied by the heat wave model is a lot more aggressive than the Lee Corder. So all in all, the difference between the one-dimensional original Lee Corder and the heat wave model depends very much on the age you consider. Okay, so it's time to conclude what we have done in today's presentation. In today's presentation, I have introduced a heat wave model for producing 2-dimensional mortality improvement scales. It is important to note that in the heat wave model, the key quantities are determined endogenously, i.e. from the available data, and these key quantities include the initial heat, the long-term improvement rates, the speed of convergence, and the blend between period and cohort effects. And finally, because the heat wave approach is purely model-based, we are able to derive measures of uncertainty using standard statistical methods. I also wanted to note that the heat wave model offers some new perspectives to longevity risk modeling and management. First of all, it redefines coherent multi-population mortality forecasting. When forecasting mortality rates of related populations, coherence is very important. By a coherent forecast, we mean that the projected expected trajectories of mortality rates of different populations do not diverge indefinitely over the long run. Now, in the past, coherent forecasts are typically achieved by using mean-reverting stochastic processes, but with the heat wave model, coherent forecast can be obtained by carefully modeling the background mortality improvement rates. We can add constraints to the background improvement rates of different populations to ensure coherence. And secondly, in terms of risk management, the heat wave model offers a new paradigm for longevity hedging. In the past, when developing longevity hedging strategies, we focused on mitigating the uncertainty implied by some linear stochastic processes, but that in the new framework, the goal of hedging should be mitigating the uncertainty surrounding the heat waves, i.e. surrounding the uncertainty concerning the heat wave parameters, mu, h, and sigma. So, that is the end of this podcast. Thank you for watching.